Hi everyone. This video assumes you've either watched the previous video on statistical uncertainties and systematic bias or are familiar with these topics in the context of performing an experiment. For a data source, consider measuring the position of a moving object as a function of time. If the object is a pendulum, many factors affect the data: movement of air, vibration of the table, and more. As we can't know the precise effect of each factor, they produce statistical uncertainties in our data. Any probabilistic process, called a stochastic process, can be described by a distribution, a histogram, showing how frequently each value was obtained, like a grade distribution. Just as we don't know the precise effect of each random factor on our measurements, we don't know the shape of each random process that generated these effects. However, remarkably, when random influences combine, as they do in an experiment, the distribution of the sum of these random effects is a known distribution. Can you guess the shape of the distribution that describes measurement uncertainties? We're going to test this remarkable claim that we can know the shape of measurement uncertainties, even when we don't know the distribution shapes of each factor contributing to measurement uncertainties. We'll test this claim in two ways. First, using a Python simulation running in Google Colab. In this simulation, we'll select 4 distributions. Sample values from each distribution will be summed, and sums will be binned to form a histogram. This process will be repeated for many trials. We can select up to 10,000. The distributions we can select are normal, also called the Gaussian distribution, uniform, exponential, and gamma. Now, obviously, if we start with normal distributions for all 4 distributions, it'll be no surprise if the distribution of the sum of the values sampled from these distributions turns out also to be a normal distribution. And that's the case, as we see here. The real test of our claim will be when we set the 4 distributions to something other than normal distributions. As an extreme test, let's select uniform, that is completely flat distributions to sample from. We'll sum the samples, repeat 10,000 times, and look at the resulting distribution. As you see, remarkably, even if we start with uniform distributions for each random effect, when their contributions are summed, the distribution of the sum of these random variables is a Gaussian, that is a normal distribution. Now, I can't see you from here, but if your jaw hasn't dropped, you may not be getting just how remarkable this result is. Let's watch these 2 simulations again, but in real time. First, with all 4 distributions selected to be normal. This time, with all 4 distributions selected to be uniform. It's possible that you're thinking, well, this works in a computer simulation, but does it work in the real world with real experiments and real data? So here's an ultrasonic motion sensor, a device that generates and sends ultrasonic waves to an object and detects their reflection to determine the distance to the object. In reality, the ultrasonic motion sensor is just an ultrasonic generator and a clock. The device is programmed with the speed of ultrasonic waves in air at room temperature, so by measuring the time interval between sending and receiving the waves, software calculates the distance to the object from the simple kinematic expression that the distance delta x is equal to the average speed times the time interval. As an aside, this example illustrates an important principle in experimentation, that usually we can't directly measure the property we're interested in. In this case, we want distance, but can only accurately measure time. So we indirectly obtain distance from time. To demonstrate how general the result of our computer simulation was, we'll use no special setup in our physical experiment, just an ultrasonic motion sensor resting on a tabletop aimed at the ceiling, a popcorn ceiling with an irregular surface, as you see in this center image. We'll bin the data to form a histogram and observe the resulting data distribution. Let's start. By the way, the sounds you heard weren't ultrasonic waves. The motion sensor generates ultrasonic waves in bursts, so the clicks you heard were the device turning on and off. Again, we find a Gaussian. Now, consider all the random influences on this experiment: vibration of the tabletop, air movement again, and this time also the irregular ceiling surface. Yet, remarkably, without knowing the shape of the distributions of these random factors, they all combine to form a Gaussian. This result is called the Central Limit Theorem, a foundational result in statistics, that the distribution of the sum of random variables tends towards a Gaussian under reasonable assumptions of a sufficient number of independent samples. A sufficient sample size of around 30 is often quoted, but depends on the shape of the underlying distributions, which, if themselves are Gaussian, would require a smaller number of samples. While not proving, but having established the plausibility of the central limit theorem through both numerical simulation and through experiment, from this point forward in these videos, we'll assume measurement uncertainties are Gaussian. This powerful assumption will enable us to construct an entire methodology for analyzing experimental data, from performing parameter estimation, that is curve fitting, to model testing, as we'll see in a later video. Thank you for watching.